In this video, we will continue to talk about object-oriented programming, and in particular, we will talk about templates. Templates are generally used when we have some code that makes sense with variables of more than one data type. For example, a double, an integer, and so on. The code could be in a function or in an object type, such as a structure or a class. For example, a vector makes sense with all kinds of data types, like doubles, integers, characters, strings, and so on. In this module, we will focus mainly on template functions. A problem we want to deal with is how to call functions with different variable types. We have already covered some methods for doing this. For plain data, a single function can accept arguments of other types by automatic conversion. For example, here we have a function that calculates the square of a number, and we assume here that the argument is a double and the output of the function is also a double. So if we pass a double, that's fine. So we have a double a here, and we call that function square to calculate the square of a. That works fine. If we pass an integer, however, then there will have to be some conversion from integer to a double data type. Now, this can happen automatically, but it may lead to errors, or it may not be possible at all. So, in this particular case, if we have defined a square function with an integer input and integer output, but we try to pass a double to it, then that can be dangerous. For example, this number 2.5 may get rounded to 2 to the nearest integer, or to 3. And then we may get 4 or 9 as a result. So I would ask you to try and run this code and see what result you get. Even worse, sometimes automatic conversion may not even be possible. For example, a vector of integers and a vector of doubles are different data types, and we cannot convert between them. So, for example, the following code will not compile. Here we have a function double sum that takes a vector of doubles as input and calculates the sum of all components. And if we try to pass a vector of integers to this function and calculate the sum, it will not work. The compiler will give an error. We have talked before about function overloading. So we can have multiple functions for each data type, or one function for each data type. These could have the same or different names. If they have the same name for function with a different type, so function with different argument, then that's called overloading. Here I'm overloading the square function. So here I'm telling the compiler that if the argument is an integer, then use this function. If the argument is a double, then use this function. And the output is an integer or a double, respectively. Now, there are some disadvantages of multiple functions. First of all, there are many inbuilt data types, like integers, unsigned integers, long integers, unsigned long integers, long integers, and so on. Also, if we change the way the function works to a more efficient or a safer method, we have to go back and change this in multiple places. So this is hard to maintain. A general principle is do not repeat the same code in multiple places, because sooner or later this will lead into different versions of the code and conflicts. And of course, it's very hard to maintain. A better practice is to write the code once and make use of this from different places. The solution that was implemented in C++ is template functions and data structures. In the following code, an integer appears in two places, as an argument and as the return type. We want to replace this with a placeholder that stands for any variable type. So here t is the placeholder. We declare that using the command template and then type name and then the name of the placeholder or the name of the template we want to use. And then instead of saying double square constant double x, we simply say t square constant tx. And then t can be anything, can be a double or an integer or any other data type. The command template tells the compiler that a template function follows. The command type name tells the compiler that the next symbol, t in this case, is the variable type to be substituted. The word class can be used here instead of type name. The t here is an arbitrary symbol that stands for a variable type. We could have used any name, it's just a placeholder. T is conventional when there is just one type to substitute. Now, this solves the problem we mentioned before. So in this example, we call a template function instead of an overloaded function. Now, this template function can be called and it solves the problem we mentioned before. So we don't have to use overloaded functions anymore. In particular, we can call this function with arguments of different types. For example, here we have declared this template function square, and then we can call it when the argument is a double, like x 2.5. We can also call it for an argument that's an integer, like k, which is equal to 2, and it will work correctly in both cases. Now, here's what the compiler essentially does in this case. For each data type that we call the function with, the compiler generates a function. So in the previous example, the compiler automatically generates the following functions. This is a square function with a double argument and a double output. And this is a square function with a constant integer argument and an integer output. So it is creating an overloaded function, but we don't have to repeat this code ourselves. The compiler does it automatically. For this to work, the code has to be correct C++ when the t is replaced by whatever data type we call the function with. Remember, t is a placeholder. It can be used for double, for integer, for long integer, any data type. So the following will not work if we call this square function and use a string as input, for example, because this star, the multiplication, is not defined for a string. So this will not compile, we will get an error. We can also use template functions with a vector, which can hold different data types. Now, remember that this sum, this function that calculates the sum of the components of a vector, we have declared here that the input is a vector of doubles and the output is a double. And this function will not work if we call it for a vector of integers. we can replace the specific data type that the vector contains with a template type. So here we have a vector double and the output is a double. We can replace those. So we can write vector t and then the output is t, and that's the type. So the type that we have as input here is the same as the type of the output, and of course we have to declare the type name here, t, which is our placeholder, and again t can be anything. In this way, remember we also have to declare ts here. In the previous example we had defined a double s, which is the sum, and then we return that number s, and here it's not going to be a double necessarily, it can be an integer or anything else, so we have to say ts and then return the quantity s in the end. Now in this way, this template function will work for any data type. By any, I mean any appropriate data type. It will still not work for data types for which, for example, the plus is not defined. So the following will now work. We have declared this template function sum as shown here, and the remaining of the code is in our main function. We can call the function for a vector of integers v, and we can also call it for a vector of doubles w, and then calculate the sum in both cases, and in both cases we will get the correct result without round errors and without doubles getting rounded to integers and so on. Now the previous examples are template functions. C++ also has template data structures. One example is the vector that we've been using. There would be one set of code for this in the standard library with a template parameter like the one we used, t, and that would standing for integer, double, and so on. So there is something in that library of the form template, and then type name t, and then class vector. We will not do this ourselves. We will just use the vector for this module. Now that's it for this video. In the next video, we will illustrate how to use objects and like structures and templates when doing numerical computations. Thank you for watching.